Welcome to my talk at the IEEE Sensors Conference. My name is Ayman Mohamed, and I'm a PhD student at the Institute of Smart Sensors at the University of Stuttgart in Germany. Today, I'm going to introduce you to our low-noise CMOS sensor front-end for a TMR-based biosensing platform. As the name suggests, biosensor is a biological sensor. It converts a biological or chemical quantity into an electrical, thermal, or optical signal. Biosensors can be used in medical disease diagnosis. This is done by detecting biomarkers present in a certain sample. A biomarker is a molecule that indicates a certain biological state or disease. This could be antigen, antibodies, proteins, or DNA. While ELISA being the gold standard for commercial biosensing platforms and used in labs for diagnosis, they rely on using bulky microplate readers as shown on the right side. This unfortunately doesn't help in integrating such systems for point-of-care settings. Also, ELISA suffers from autofluorescence, setting a limit on the achieved signal-to-noise ratio. Alternatively, magnetic sensors are a strong candidate for biosensing platforms, since samples lack any magnetic signature reducing background noise. In this work, we investigate TMR-based biosensing platforms, which aim to enhance the limit of detection while providing a point-of-care solution. A tunnel magnetoresistive sensor, or TMR sensors, consists of a free ferromagnetic layer and a pinned layer. An insulating barrier between both layers is also added. And now when an external magnetic field is applied, a change in the magnetization of the free layer is observed. Consequently, the electrical resistance of the TMR sensor changes. In order to functionalize the TMR sensors for the biosensing experiments, the following procedure is usually carried out. First, the TMR sensor is coated with capture antibodies. Afterwards, the targeted biomarkers in a certain sample are specifically binded to the capture antibodies if they exist. Third of all, detection antibodies are added and the sandwich structure is formed. And finally, paramagnetic nanoparticles are added to the structure, providing the signal for the TMR sensor. To obtain this signal, we need to apply an external magnetic field in the non-sensitive direction of the TMR sensor. This field excites the nanoparticles, which produces a field change that's sensed by the TMR sensor. The change in the sensor's resistance is proportional to the signal. Measuring the change in resistance corresponds to finding the biosensing signal. However, measuring the change in resistance is challenging from the readout point of view for many reasons. First of all, low power is needed for point-of-care applications, and hence we designed a low-power integrated circuit for the readout chain. Second of all, the biosensing signal is minute compared to its base resistance. In many scenarios, this could be in micro-ohms regime compared to kilo-ohms of base resistance, and hence we implemented a differential readout architecture by including a reference sensor covered with epoxy. This should remove the problem of having a large base resistance. Third of all, large DC offsets due to a large magnetoresistive ratio of TMR sensor or sensor's mismatch or temperature drifts or undesired external fields can be observed. Hence, we continuously monitor the DC offsets and we calibrate them. And finally, 1/f noise limits the overall performance of this design. And hence, we modulated the excitation field at a frequency higher than the 1/f corner frequency of both the TMR and the readout chip. This graphic shows the block diagram of the readout chip, as well as the micrograph of the manufactured ASIC. The ASIC has been manufactured in 180 nanometer SOI technology. The proposed DC-coupled readout scheme monitors and calibrates any offset while providing a gain of 1000 or 60 dB for the biosensing signal. The first stage provides a low noise gain of 50, and the second stage with gain of 20 provides the driving strength for further off-chip signal conditioning electronics. An 11-bit DAC biases the TMR sensor and provides a first-order compensation of any offset in the front-end electronics or between the sensor and its reference. A second 5-bit DAC is connected to the output of the first voltage amplification stage in order to cancel any residual offset. And now I'll be explaining into details the first amplifier. The amplifier is implemented as a fully differential difference amplifier with Miller compensation. The total gain of this amplifier is 50. Current reuse architecture is used at the input stage. This is done to improve the power efficiency. As seen here, PMOS transistor and an NMOS transistor are stacked on top of each other to increase the power efficiency. A common source output stage with a diode connected load is implemented. This is done in order to buffer the output voltage to the next amplification stage. Now moving on to the sensor biasing. An 11-bit current mode binary weighted DAC is used to compensate offsets. One important design decision is the sizing of the DAC unit element based on its noise requirements, since the noise of the DAC is directly added to the input of the system. The current noise power spectral density is shown as follows. However, it's proportional to the transconductance, or GM, and inversely proportional to the size of the transistor. Hence, the transistors are designed to work in deeply strong inversion. This is done by minimizing the GM over ID ratio using very small aspect ratios of the transistors to achieve such conditions. In this design, a DAC unit element has the size of 850 nanometer over 80 micrometers. The chip has been tested and characterized using a custom designed evaluation platform. A TMR sensor with a nominal resistance of 830 ohms and a sensitivity of 93 ohms per millitesla using a biasing current of 1.1 milliamps is used. The sensor dimensions are 6 × 4 millimeters square, and it consists of 1,102 sensors connecting in series. This is done in order to lower its 1/f noise. Magnetic fields in the sensitive direction of the TMR sensors are generated. This is done using custom designed Helmholtz coils wound around a 3D printed holder, as you can see on the right side. The input refer thermal noise floor of the entire system is 9.5 nanovolt per square root of hertz. This corresponds to a limit of detection of 300 picotesla per root hertz. It's worth mentioning that the input refer thermal noise floor of the chip on its own is 7 nanovolts per root hertz. The flicker noise 1/f corner frequency is extrapolated to be 7 kHz. And now the AC gain is 60 dB with a measured bandwidth of 500 kHz. This bandwidth is sufficient to modulate the TMR signal outside of the system's 1/f noise by field modulation, or in our case, to modulate the signal over 7 kHz. The linearity of the entire system is also characterized. This is done by measuring the spurious free dynamic range of the overall sensor system. The measured SFDR is 64 dB for an input signal of 1.35 millivolt peak at a frequency of 5 kHz. This very good SFDR is due to the current biasing of the TMR sensors. And this is because the TMR's resistance changes more linearly than its inconductance in response to a given magnetic field change. We've also evaluated the chip's capability to bias largely different sensor resistances. To this end, we have replaced the TMR sensor by a potentiometer and recorded the input referred voltage offset for different resistances after applying the automatic on-chip calibration routine. And the chip can successfully calibrate resistance between around 500 ohms and 4.8 kilo ohms. This means that the chip is compatible with the large process variations of TMR. The chip's stability over time is also tested for 30 minutes, which is sufficient for all practical measurement conditions. The system is sufficiently stable, and calibration during biosensing measurements can be avoided. These experiments have been carried out without any magnetic field shielding. In conclusion, we've presented the low-noise readout chip for TMR-based biosensing platform, featuring an input refer thermal noise floor of 7 nanovolt per root hertz and a gain of 60 dB. The presented chip paves the way towards point-of-care applications because of its low power compared to discrete electronics, its capability of biasing different sensor resistances, and its stable operation over practical measurement conditions without needing any magnetic shielding. We're currently characterizing the complete platform, where we started with 6 TMR sensors that are multiplexed and processed using 2 of the implemented ASICs. This platform is designed to be operated only by a single power supply socket, paving the way towards a point-of-care setting. Afterwards, we're going to perform biosensing experiments on the proposed platform. And finally, we're looking forward to integrate our platform in high-performance point-of-care disease detection systems. Thank you for listening to my talk, and I'm looking forward to the online discussions.